Sure. So I prepared some presentation. Feel free to interrupt me anytime. I mean, if you feel that your question that you prepared relates to the slide I'm discussing, then that's perfect moment to interrupt and talk about it. So just one thing about some questions on the Telegram. What I prepared basically is mostly about stuff that was in the book with some additional thoughts, although it does not cover the question, how do you translate a program into arithmetic circuit? I mean, I know that it's possible in theory. We talked a bit about it last week, but I think it's a very good topic for a separate talk, which I would really like to listen because I'm not sure how it's actually done in practice. Yeah, we can talk a bit about this, but I'm not gonna be able to answer questions related to that. Okay, let's get started. So first, a quick recap on secret sharing. So the task here would be to split some secret S into n parts, so there are n people, in such a way that any t of them are enough to recover the secret. But if you have only t minus 1, then you will not only not recover the secret, you will not be able to learn anything. And the classical way to do it is to sample a random polynomial where such that f of 0 is the secret and all the rest of the coefficients are totally random. It's polynomial over the finite field, so your secret should be somehow cast into a finite field. Then you send evaluations of this polynomial to some committee, some n nodes, and then anytime t of these nodes gather together, they will be able to recover the secret using Lagrange interpolation. These lambdas here are Lagrange coefficients. I'm not putting the form of these coefficients. I mean, it's pretty standard and can be found on Wikipedia, and it's also complex enough to not discuss it in this talk. So I hope anyone is up to date with the sharing, so we can go to the actual protocols. First, how does it work in general? So let me just move the window. So in general, you want to translate your program into arithmetic circuits, which is a very interesting topic by itself. I'm not sure how to practically do it, as I mentioned. And then once you get it, it works like this. All of the inputs of the program you want to have shared among some community using secret sharing. And then you will compute each gate separately. And what does it mean to compute each gate? So if you have an addition gate and you have two inputs which are shared using secret sharing, then what you do, you run a protocol to get output of this particular gate, also shared by means of secret sharing with the same threshold. The same goes for the multiplication gate. So gate by gate, you compute the whole circuit. You don't necessarily need to do it sequentially. I mean, for example, here you possibly could compute the plus and the multiplication gate in parallel, although this one will require additional rounds. So basically, the intuition is that the number of rounds that you will need to use is generally proportional to the depth of the circuit. So, and you use some threshold t, that's important. So for all of the secret sharings, you want to use the same threshold t. And once you get the result, initially the result is shared with the same threshold, and then you probably want to reveal the result. So you like all the parties just publish their shares, and everyone can compute the result of the computation. So I have another slide where I have some comparison to YAO idea. And it's biased. I mean, I'm a big fan of secret sharing and not so much of YAO. So, and I think that there are some arguments why this design fits blockchains better. So what happens in Java circuits is that in the basic idea, you've got just two parties and can be generalized to more parties, but the rules stay the same. And for two parties, it works like that. You've got Alice and Bob. Alice has some input 1, Bob has some input 2. It can be a group of inputs, doesn't matter. And they run the protocols among themselves. So if you would have like 5 nodes with 5 inputs, they would just run the protocol among themselves. And this is okay in some applications, but this is not really, I mean, it's not immediate how to put such a thing on blockchain or how to use blockchain to scale it. I mean, if you, for example, have a program with, if you would like to conduct a voting, for example, a private voting among 1,000 parties, then there's no easy way to, I mean, you would need to run Java circuit among 1,000 nodes, which is probably unfeasible. And there is no way to, no simple way to push the computation, the actual MPC protocol to some other parties, to some, you know, blockchain guys or whatever. So the parties which are running the MPC needs to be the same parties who, I mean, needs to know the inputs. And I mean, in my opinion, it's a major obstacle when it comes to blockchain deployment, because what you would like to have most probably is more like this. So there is some number of guys like the blockchain guys, some kind of a MPC committee, and then you've got users which are separate. So Alice and Bob in this scenario have some secret inputs, and they send shares of these inputs to the MPC committee. So no one in the committee actually knows the inputs. Each of the guys in the committee only knows one share of each of the inputs. So the inputs remain private, remain known only by users, but the whole burden of computation is put on the committee. So even if you would have 1,000 of Alice and Bobs here, this is still all right. I mean, they can share their secrets among the committee of 5, of 10, or what have you. Then only this committee will perform the expensive and long computations, and then they would either push the result on blockchain or send it back to the users or well, whatever. So so as I said, it's got, I mean, I'm open to discussion here. If anyone knows an idea how to use Java circuits in a similar blockchain paradigm, and then I'm be very interested to hear that. But this is pretty straightforward. So that's why Damian last week mentioned that also he believes that this is more fit to blockchains. So I guess this would be the argument which he had on mind. I don't know if anyone has questions to that or some comments. I can just keep going. Okay, so this is the beginning, and now we need to show how to compute each of the gates. So there are 2 types of gates. Actually, I'm going to show 3 types of gates because I'm going to show multiplication by a constant as a useful operation, which could be a gate as well. So first, the addition gate. This is the simple case. So you've got 2 inputs which are shared by secret sharing with threshold t, and you want to have C, the sum of these 2 inputs, which is also shared with the same secret sharing. So this is actually very simple, because what you can do, what each party needs to do, is to just add their shares. Remember that the shares correspond to polynomial evaluations. So you've got polynomial A evaluated in some point and polynomial B evaluated in some point. And the secret is the same polynomial evaluated in 0. So what effectively happens here is that you just add the polynomials to get the polynomial, which which 0 point is the sum of 0 points of previous polynomials. And with various argument that this is random enough. I mean, assuming that the previous sharing was random, the next sharing is random as well. So this is pretty straightforward. I mean, is it understandable for everyone? Anyone? At this point, I'm wondering whether I'm even online, so I'd appreciate any comments.
Crystal clear.
Okay, great. Thank you. So the second thing, it doesn't differ all that much. It's multiplication by constant. So so we've got A shared by secret sharing. You've got publicly known B0. And you want to have C, which is shared and equals A times B. So again, each party locally computes B0 times A, and that corresponds to multiplying polynomial by B0. And that works for the same reason as before. And now we come to the tricky part. The tricky part is multiplication gate. So again, we've got two secrets shared with secret sharing with threshold T. Sorry, it's F here. It should be T. And we want to have secret C shared among the same party. So we can approach in the same way. I mean, everyone could, for example, multiply by shares, and that's all right. That corresponds to polynomial multiplication, but there is a caveat here, because you've got two polynomials of degree T, then multiplying it, you're gonna have polynomial of degree 2T or 2F. So why is it problematic? Because it's a secret sharing with different thresholds. So you will need 2 times more nodes to actually recover the secret. And while it may be all right for a single multiplication gate, if you've got a circuit of depth, I don't know, 5, then these thresholds grow quickly. So at some point they can be bigger than n even, which doesn't make sense. So what we need to do to make this work is to have some tricky way to lower the degree. So this is what we are going to do. That what's written here. I mean, we are actually going to multiply the polynomials, and then we're going to perform some trick to lower the degree of such polynomial of degree 2f. So there are multiple ways of dealing with degree doubling. The BGW is perhaps one of the simplest ones. So, like, the setup for a problem is that we have secret sharing with threshold 2T of some secret C via some polynomial C. And what we want to have is going to be a protocol. So what we want to have as an outcome of such a protocol is secret sharing with threshold T of the same secret using some different but also random polynomial. So beware, there's some complex high school mathematics ahead. But it's not that complex as it looks like for now. So what is kind of 2 steps, although it translates to just one communication route. So we're gonna look at it from the perspective of party K, which has some share of this sharing. And the sharing is such that, the share is Ck, it's an evaluation of polynomial C, and the polynomial is such that C from 0 can be recovered by Lagrange interpolation. So the step 1 here is that party K shares its share. So it's going to be a lot of sharing here. Each of the parties needs to take its own share and share it among the whole committee. So each share is a polynomial evaluation, and each party samples a polynomial to share this evaluation. So what party K samples is polynomial Fk, and it sends f of 1 to f of n to respective parties. And the polynomial is such that Fk from 0 is Ck. So it's a proper secret sharing of Ck, although it's with threshold t, not a threshold 2t. So each party should do that. Some parties can crash, and that's okay. Let's not focus on that for a moment. Let's assume that all the parties are done with such sharing. So now what party K does, it computes its final share, which is dk times the evaluations of the respective polynomials. So polynomials of each of the different parties multiplied by Lagrange coefficient. And there is this tricky equation here. Although, I mean, you can read that. It should be all right. I spent some time. I mean,
the first summation, the upper bound shouldn't be just t.
Yes, it should be t. Sorry, that's a mistake. I spotted that mistake, but this is not so easy to fix as it's not done in the PowerPoint. You're right. That should be just t.
Lambdas are different. Yes, they depends on the polynomial.
The lambdas actually depend on the subset of parties which you get. I mean, lambdas depends on the evaluation points.
Yeah, but lambdas that are next to f depends on sharing the secret. No f. So f, the index in f. So fk. Yeah, so lambdas that are next to f depends on the index which is the lower index of f.
Wait a moment. Yes, sorry. Indeed. I mean, this equation assumes that in both cases you got the responses from the nodes with indices from 1 to t. It may not be the case, so in the different scenario, the lambdas would be different. You're right. I'm sorry for that mistake. This is kind of simplified. Anyway, this thing follows from the linearity of each of these operations. So how to think about it is that having one share of each of these polynomials, I mean, if you sum up all the shares everyone got with the respective coefficients after you figure them out, you should get CKs, and from CKs you should get C0. So this is a bit tricky because you've got two different lambdas here, as you noticed, although everything's linear. So so after you do that, you should be able to recover C0. And what's important here is that these things are shared with a threshold t. So now it's enough that you got. Yeah, this equation is not very good. I'm sorry for that. So that should not even be 2t, that should be t. And different lambdas. I'm really sorry. So what's important is that one of the sharing is with threshold t. So now it's enough that you gather t of the shares to recover all 2t plus 1 CKs, and from them you can recover C0. And like when you use the linearity, that actually translates to computation on decays. Yeah, sorry for this question, it's a bit misleading. But in general, this approach gives us T sharing of secret C. But it's got some problems. I mean, the main problem with it is that there is quite a lot of sharing here. So you need to share each of the shares, which translates to O of n squared total communication. And while some nodes can die, no node can cheat here. I mean, it's enough that just one node lies about its sharing and just puts some random numbers everywhere, which are not connected to its initial share, for everything to just break. I mean, you're gonna have just random output instead of the correct one. So this is really not adversarial friendly. I mean, it is adversarial friendly in the sense that an adversary can cheat very easily. It supports semi-honest adversaries well. So if the adversary is following the protocol and just wants to learn something about the secrets, he's not going to be able to do it unless he controls over T of the nodes. So yeah, BGW works with semi-honest adversaries only. And that's it about BGW. There is one more very useful trick that I want to talk about, it, and that was in chapter 3.4, and that is multiplication triples, or Beaver triples, in other words. So the idea is that even before you get any inputs to any programs you would like to run via MPC, you can prepare for it. So the committee, which will be responsible for computing the MPC, can compute just triples of shared values where A and B are random and C equals A times B. So they kind of compute only multiplication gates on random inputs. And later on, as it will occur in the moment, they will be able to use it to speed up the whole process. Because again, this thing, the multiplication gates, requires quite a lot of communication, while the other things are basically local. I mean, they require only local computation. So if you've got an arithmetic circuit and you want to just compute it without multiplication triples, you only the multiplication gates are going to slow you down, basically. So for now, assume that you have it. How to get it, that's, I mean, the whole problem in MPC basically can be reduced to how to get Beaver triples quickly. So for now, assume that we get it. So we assume that we have X and Y and Z shared, so that, oh no, sorry. As I wrote here, we have A, B, and C shared among the committee, so C equals A and B. And now our goal for the secrets X and Y is to compute Z, which will be a sharing of multiplication of X and Y. So we want to compute the multiplication gate on X and Y using Beaver triple ABC. So again, there is going to be some complex high school computation here. Hopefully this time it's going to be correct. So what happens is for each party is that it reveals xk minus ak and yk minus bk. So note that while these things, x and y, we would very much like to keep them secret, A and B are random, and no one knew, and no one will ever know what was the value of A and B. So revealing only x minus A and y minus B is not actually going to reveal x and y, and also not going to reveal A and B. So after enough parties reveal their shares for x minus A and y minus B, anyone can compute the actual secrets, x minus A and y minus B. Keep in mind that x and y are secret still. And then party K can compute this complex thing. So here I color-coded the shares, so they differ from the actual values which are known in the plane. So after this reveal, everyone knows what's x minus A and y minus B, so we can just use this as constants, and these are shares. So to compute zk, which is the new share of party K, we need to multiply two constants. That is obviously very easy. you need to multiply your own share via constant, which is also easy because that's the multiplication by a constant gate. So this is the local operation as well. Here is the same, and here you just put your share from the multiplication triple. And now, why does it work? I mean, what's all this equation about? So if you would reveal the secret, ZK, then you would get something like this. So like all the constants stay the same and the shares translate to actual secrets. And when you actually multiply all these things, then the most I again color coded the things which are the same. So the only tricky thing here is that we use that C equals B times A. So basically everything reduces to X times Y. So we get what we actually wanted. So the secret Z equals secret X times secret Y. And the important thing is, as I noted before, that computing ZK is purely local. So once we have a multiplication triple, we don't even need to talk to anyone to perform a multiplication gate. So if we, I think I have another slide for that. Yeah. So the whole reasoning behind it, why this multiplication triples are nice, is that you can do some preprocessing, which maybe is a bit complex. It requires O and square communication, but you can do it beforehand. And you can create lots of such triples. And then the actual computation for each of the circuits is pretty, I mean, it's very fast. It requires only local operations of each of the nodes. So yeah, so it's nice. And the second, I mean, they noted that this scheme actually does not use any, I mean, does not use the form of this sharing. So you could possibly do the same for some exotic secret sharing, which may be nice for some use cases. Maybe another benefit is that this problem could be potentially simpler than computing the multiplications gate normally, because what you want is you want to indeed have some secret C, which is multiplication of two things, but these two things you want to have random. So in theory, you could have some tricky protocol which simultaneously samples some random things and outcomes also the multiplication of it. It's not that you need to have multiplication of two specific values. It can be basically anything as long as you assure that these things are random. So this, I mean, creating Beaver triple potentially could be simpler task than performing normal multiplication gate. That's all for what I have for presentation. So it would be nice to go through the questions now. Again, sorry for the noise. At least for me, it was a bit annoying. I'm not sure how it was for the rest.
Oh, thanks for the presentation. That was great, and it wasn't too noisy.
Okay, so perhaps I was just speaking faster due to that because, well, yeah, I thought that I have to. Definitely pumped my heart rate.
So I think about the question that I had before this. So how do we go from a circuit or a program? How we generate the circuit? And I think so. Kev answered some of my questions there. For example, how to, if we want to do more things than just multiply and add, what other operations we can do?
Well, so in theory, as far as I know, you can do any operation, but some of them are going to be, I mean, expensive. For example, if you want to have inequalities, it's gonna be a bit tricky, and most probably you will need to code each number using log n secrets. So some things may require tricks like that. So if you want to have, for example, inequality, the only way I heard how to achieve that is that you need to take each of your inputs, and I mean, you will need to have some maximal number, so all the inputs are below it, and some of the inputs is below it, and so on. And then let's say the logarithm of that thing is like 8. So you split each number into the binary form, and you've got each of the digits of the binary as a separate secret. And then well, you can do inequality. Still, it's not trivial, but that's probably like an exercise to do at home. But I think there is no known way to do it like easily with normally shared secrets. So I'd assume that operations like shift can be also a bit tricky.
Well, Kev said bit shifting is simply multiplying and dividing by 2, or a power of 2.
So shifting to the left is easy because you just multiply by 2, but shifting to the right is quite hard because it's dividing by 2 and taking the floor, which in finite fields is not so easy. So yeah, I guess you would need to decompose it into bits, as Adam said, and then, you know, you can, like, every kind of computation you can bring down to the like gate level and think about Boolean gates, right? So then, like, every Boolean gate is an arithmetic operation. Actually, if you think about, like, you can write down every Boolean gate as like 2 or 3 arithmetic operations in the field, where you just treat a 0 element in the field as the 0 bit and 1 element, like the unity, as the 1 bit, and then you can do everything using arithmetic in the field. But then you, like, everything is more expensive, and actually you need multiple elements, multiple field elements to deal with one variable in the program. So it becomes expensive. But you can do everything. Like, if you think about it, if you think about variables as sequences of bits, then you can do all computations on bits. So at least conceptually, this is something you can use to kind of convince yourself that it works, that everything can be done. But of course, it will be kind of heavy.
Yeah, the arguments I've seen that the arithmetic circuits can cover all programs is by reduction to the Boolean circuits, which is, well, it's nice from the theoretical perspective, although one could expect things to be easier on arithmetic circuits than Boolean one. I mean, they kind of intuitively are more expressive. So reducing the problem to Boolean is obviously like not lossless.
So by Boolean circuits, do you mean that the field is 2 to the power of k or something like that? Or only the field is 0 and 1?
I think the only field is 0 and 1, and you've got Boolean gates on that.
I mean, normally, if you say Boolean circuits, you don't even think about a field. You just think about, like, really these things that you print on a, I don't know, you know, you think about real circuits that you can print. Okay. Yeah, just don't think about any algebra. You have like AND gates, OR gates, and stuff like that. Just think as them as like signals, 0, 1 signals.
Okay, and I just have a last question, because so division is not easy, right? Or
I mean, division is multiplication by the inverse, right? And
okay, so in Shamir we have an inverse, I guess, because it's a prime field. But
not. I'm not. I mean.
But I mean, is that always? Do we not have to?
Can you hear me?
How do you find the inverse then? I mean,
I'm not sure.
Finding the inverse is, you can do it like in 2 ways. One way is inverting a number is just raising it to the power p minus 2. So there is this formula, it's called Fermat plus Fermat's little theorem or something like that, which says that if you raise the number in a field modulo p to the power of p minus 2, then you get the inverse.
But that's expensive.
You can just do that by multiplication. You reduce it to multiplication.
Okay.
But there is also the other trick that you can do it using 2 multiplications actually. But yeah, anyway, you can do it using multiplication.
Yeah, Jonas, can you hear me?
Yes.
Yeah, I think your question, it depends. Do you want to compute the inverse, or do you want to show that there's an inverse that exists and the multiplication equals this thing? If it's the second one, then you can compute the inverse out of the circuit and then just multiply it by like if you want to do x divided by y and you have y, you compute 1 over y out of the circuit, then you do y times 1 over y is equal to 1, and then you do x times 1 over y. But
Okay.
it's a bit more, yeah, if you want to do it inside of the circuit, then you'll need like a inverse algorithm in the circuit, which is a lot more expensive.
No, the thing is, it's not more expensive. It's actually the same as multiplication. There is a simple trick which allows you to reduce it to multiplication.
Oh, wait, so there's 2 situations. If you want to compute it inside of the circuit, so you'd need to use an inverse algorithm.
No, so what I'm saying is the inverse algorithm is simple. It's just as simple as multiplication, okay?
No, I don't think I understand. Because I understand when you said 2 multiplication gates, that makes sense. But if you want to compute the inverse inside of the circuit, I believe it's
so
more
what
expensive.
I'm saying, what was not presented here, but what can be done is that there is a simple trick which allows you to compute the inverse inside the circuit by using, I don't know, 1 multiplication and 1 random element, something like that. But yeah, it's hard to explain without proper slides, so I will not do that.
But it's a way to create a division gate or something, right?
Right, yeah, you can do a division gate.
Yeah, for division, I'm not sure I quite understand. So if I want to do Fermat's algorithm inside of the circuit, are you saying that it takes 2 gates or?
No, I am not saying this. So I am saying this is one way to do that. This is one way to convince yourself that this can be done, okay? But this is not the most efficient way, because this would require like log of p multiplications. So it's not quite efficient. But you can do it in a different way, which would require 1 multiplication and generating 1 random sharing, essentially.
Okay, yeah, right. I think we're saying the same thing. I was saying that the Fermat's way is a lot more expensive than the first way, which is like 2 multiplication gates. But then you said another way, which includes a random
your
element.
first way is multiplying by a constant, so it's not actually solving the problem.
Yes, I think Adrian, he linked, or he sent in a chat here on Zoom a code snippet or a pseudocode snippet for how to do this. So you need a random number, then you multiply it, then you open the multiplication, then you multiply the inverse of the open value. I mean, it's hard to say on, yeah. If you look at it, it looks pretty clear.
Yeah, that's the thing.
Maybe I can share it quickly. Like that. Okay. Yeah, so I mean, maybe we can move on to some other questions unless there's more on this. Fadi also asks here. So he asks, I do not get why putting things in pre-processing is better. Talking about the Beaver triplets. I never worked on MPC, but as far as I understand, you still need to communicate the ABC sharing. Can you briefly explain shifting things in the pre-processing phase is better?
So that would be rather a practical argument that, well, once you are on the level where you actually want to deploy some kind of a solution, then it's nice to allow the committee to pre-compute a lot of things. So whenever the request will come, they will just respond quickly. And for example, if we're not gonna have a uneven income of requests, so there will be points where there will be a lot of requests and there will be points with none, like during the night or whatever. Then you can spend this night to pre-compute the next things. But it does not have a theoretical significance all that much. It's just for the practical argument, I think.
So indeed, moving things to the pre-processing phase does not have any other reasons, as you said, but there is another reason to use Beaver triples actually. So the reason is that you can pre-compute them more efficiently than you would do multiplication.
Due to the fact that these are multiplication of random things, right?
Right. And the thing is that you can sometimes, for some cases, not all of them, you can create, say, a linear number of multiplication triples at the cost of one multiplication.
This is like in this Honey Badger MPC, right?
No, this is Honey Badger MPC is like
it's using
a trick which is 20 years old, so I don't think it's it's fair to actually cite it as the source of this. But anyway, yeah. So you can pre-compute multiple multiplication triples at the cost of what you would pay for one multiplication in an online phase.
For low thresholds, I'm not sure whether it works for high thresholds.
So that's another reason why you would do that.
So you basically do not have to communicate those shares. I think I didn't get that part in the sense that, as far as I understand, even if you pre-compute them, you still have to share those shares, right?
There is a trick. We can post it later. I'm not sure, Damian, if you have a link, which allows you to do using only n-square communication end up with like O of n triples, not only one triple as it would be normally. So normally, if you want to compute multiplication gate, it requires n-square communication. And with this trick, it works only for low thresholds, like 1/3 of n, I think. But with this trick, basically paying the same cost, you get linearly more triples. So you get linearly more efficient.
I'm not sure that was the question. You can show the slide with multiplication using Beaver triples again, Adam. Okay. So I think it might clarify why using a triple is better than this BGW approach.
Sure. Wait a minute.
Because that's the main trick here.
Am I showing the slide?
Yeah. So the thing here is that you just need to do addition and multiplication by constants. If you use this idea, you don't need to do this like sharing of your shares and stuff. So this makes it much more efficient than the BGW approach. So one multiplication is just using one triple, and you do only multiplication by constant, addition, and reveal. And all these things are kind of simple. So like all the tough work is pushed to the pre-processing So yeah, still you need to do that somehow, but at least this part, like one multiplication is then very simple.
So the complexity of one multiplication here for Beaver triples are 2 times n, right? So we reveal twice. So we share 2 times n messages.
Yes.
Whereas the other one would be n squared in the normal, in the non-Beaver case. Okay.
And using these tricks for low threshold, even pre-processing can be actually done linearly if you like count per triple.
Thank you. Thanks.
Do we have more? I mean, I didn't read the Telegram questions.
Yeah. So, I mean, we can either talk about, I would like to know a bit more about this trick, how to make it linear, perhaps. That would be interesting. Or we can talk about how to make this. So this is only semi-honest now, but what is needed maybe to make it maliciously secure, if anyone knows? I'm a bit curious to that.
Someone could show how to translate programs into circuits. That would be interesting, but I'm not sure what literature would that even be. Because you're saying about the next meeting, right?
Yeah, I was saying, but now, but.
I don't think there's any literature on translating your general high-level program into an arithmetic circuit.
There is some code for sure, which is used for snark guys. So while someone coded it, maybe someone explained it as well.
Right. Yeah, I guess. Did you have more of an idea of what you wanted to see? I think the programs for snarks are quite large.
I don't know. I'd like to have like an intuition for like, yeah, how big the circuits are for average program. I mean, how basically maybe how basic operations translate into circuits and how they are stacking. I'm not sure. I know that perhaps I'm asking for something which in practice looks like a I don't know, boring dictionary.
No, I think it's quite interesting as well, how things are done.
Do you have any experience with that, Kevin?
I have a tiny bit of experience, so I could understand what you were saying about the bounds checks and maybe like cast-in, like how it's done in practice. I've seen some, but yeah, if you like, you'd have to be a bit more specific. Most of the stuff, if they're bitwise, then you have to decompose the field element, from what I've seen. So
what I think what I wanted to ask actually is that is there some kind of a library program or translator or whatever, so that I can write a program in a reasonably expressive language, and this thing will just translate it for me into arithmetic circuit, so I don't need to care how it's done.
Yeah, I think there's quite a lot of things like that, but it depends on what you mean by high level. Do you mean like C, Rust, or do you mean actually a DSL?
I mean, it would be nice to be able to write code in like C and then just don't care about anything else. But if that's possible, then it's great.
Maybe, I'm not sure, I haven't looked at it in a while, but maybe Pinocchio would work. But from what I've seen, it's best to use a DSL since they kind of safeguard you from doing quite a lot of things that are just dangerous. But yeah, I mean, I can, because I've seen quite a few of the what they're doing inside, I can kind of explain a bit. Just depends on what you want to hear. Range checks, as you said, are just done by decomposing the field element. Bounds check, the upper bound has to be known because field elements, they're not ordered. So if you want to do A less than B, for example, B has to be known beforehand, for example.
So you are unable to compute A less than B for 2 secrets?
Yeah, because A less than B in a field it doesn't make sense to, because you can just add P onto, like if you add P onto A and then P plus A looks bigger than B. Because field elements aren't ordered. They wrap around. But if you say A less than B, which I know, then you can say B is, let's say, if B is like 10 bits, then you can say A has to be less than, A has to fit it.
What I meant is like taking one step back, what is my final goal is not to have a program which runs on the inputs over a finite field. I mean, finite fields are just, a trick to make it work with MPC. What I want are normal programs. And then the question is, am I able to somehow make this work in a way where I have 2 normal inputs? The translation doesn't matter. It can be translated into log n secret if that's necessary. I just want to have inequality over 2 secrets.
Right. Is there anything like that right now? I
mean, it should be possible if you have your inputs secret now in secret inputs, and you transform them to the binary circuit, and then you run like you can definitely do a less than operator. So you would just check, whether or not or who has the first one, basically, who has the first one in the sort of binary representation of the number. You have binary 32 length, but then you would assume that you know how long the like what's the modulo what you're calculating, right? So I think something like that is probably how, well, at least how it could be done. But
so my question is, let's say I change my A and B into binary representations. And then I basically just do the same thing, but then I do P plus A, and I want to compare P plus A and B. In one case, I believe A less than B is going to say A is the smaller one, but then if I do P plus A, then it's going to say P plus A is the bigger one, even though they're the same thing. So I believe there has to be some kind of known upper bound.
What is P in this example?
It's the prime, sorry. So I usually just say P for FP.
okay, by upper bound you mean like the biggest number possible that we would consider, or
right.
So
right.
So we were saying we're doing a math modulo 2 to the power of 64, something like 64-bit numbers. Okay.
Right, exactly. Yeah. So I guess so I guess Jonas is right, because in your like normal programs you usually have data types like U32, U64. So yeah. So then 64 bits would be the upper bound.
Okay, so I don't think there are any more questions, but maybe we should think about what if someone wants to volunteer for next week to present, and maybe also what we should talk about next week. We still have what do we still have? We have a GMW, the protocol GMW section 3.2.
Yeah, the question is, are you convinced with the explanation that secret sharing is better than circuits, or do we want to explore circuits as much as secret sharing?
Well, I know that I think so. I think the modern software frameworks, for example, Scale Mamba, and I'll write them in the chat, and the MP speeds, they are sort of hybrids of both models. I think if you want to be efficient on a general level, you need to do both. So you can have like garbled circuits for the certain use cases where it's quite convenient.
Wait, speed is just secret sharing, as far as I know.
No, but MP speeds.
Okay.
Like
okay.
the multi-party speeds where they just have lots of protocols and.
Okay,
I mean,
cool.
I saw something, but I'm not an expert, but it's something like linear secret sharing to garbled circuits, which then is used for calculating either like AES or some hash functions a bit more efficiently on secret shares, something like that. I think, so I think in the end, both are probably important if you want to have a general software that works on a wider range of problems. But
okay, yeah, I'm not an expert in circuits at all, so I have to believe you.
But
I had a question about the screenshot Adrian posted. So it's the one with the inverting X. This only works with, does it work with just a circuit? I don't think there's a way, right? So if I had a circuit, maybe I could compute a random A.
So I think in this case, like this is more efficient when you have like an additive secret sharing, because it makes it easier for, like, you can generate random numbers by just having each example a random number. So this rand function is really cheap, and then it depends on the how the multiplication is implemented. But if you suppose like a kind of naive implementation, it works. I hope I understand your question correctly.
So my question was like, let's say I was doing a not secret share and I was just trying to create a proof using something like ZK snarks or something like this. And I had some way to get this random A. Let's say I just used maybe fiat Shamir to just take out some random element. And then I did a multiplication gate by X. How would I proceed?
So that's a good question. I haven't really looked at it in the context of these circuits.
I don't think it will work for snarks because this A needs to be secret. Like if you like generate it in the plane, then I don't think it works.
Right. But even if A was, let's say A couldn't be secret, how would the open algorithm work?
So, I mean, if you these functionalities, you can see, I think they're called like the arithmetic black box functionality. So this is what would be provided, for example, by these frameworks like SPDZ or Mascot, I think.
Right.
And so the implementations would depend on like what security is guaranteed by these frameworks. So if you want to guarantee, like I think in SPDZ, they have these MACs, which are associated to each secret sharing. So during the opening phase, everybody would reveal their share to each other, but you would also calculate the MAC and make sure that is consistent.
Right. Okay. Right. Right.
By the way, this algorithm also exposes if or checks if x is actually 0. I mean, additively shared x is 0.
So the thing is, you need to assume that the field is large enough and that rand actually outputs a randomly shared random element. And then you don't have this issue. But you need to assume that the field is large.
Right. Okay. Yeah, that makes sense. Yeah. All right. Yeah. Thank you.
What I meant to say is that this algorithm, if executed down to line number 3, shows or exposes if x is actually was actually 0. So that it probably addresses questions about how to implement inequality. So it seems like to get equality or inequality, we just need to implement multiplication.
Did you say to get inequality and equality, we just need multiplication?
Well, inequality is basically opposite to equality. And equality is a result of subtraction. And negation is also a very trivial operation in secret sharing. So that to compare two numbers, just negate one of them, just to make a sum. And then send the sum through this algorithm down to line 3. And if it's 0, then the initial numbers are equal.
0, then the initial numbers are equal.
So if vector of A and vector of B, and suppose A is equal to B, then you do minus B, you make minus B, then you add them in a trivial way, and then get this X, and then you send this to the algorithm.
Oh, right.
You get 0, and you get 0,
Right.
but you don't expose any parts. Yeah?
Right.
So they all remain private. So both equality and inequality can be implemented using the multiplication gate, and of course the random.
Right. Yeah, I think this is how it's done in like circuits for SNOCs as well. If you want to choose, like, if you want to show that A does not equal to B, then you can just do A minus B, and then try to invert A minus B.
And we shouldn't expect any problems with the negation in the field, do we? No, I don't think so.
Negation.
I mean, B to minus B. Yeah. Okay. Yeah.
Right.
Now, by the way, sorry, I just put myself on mute. I would like to share with you the link to one of works of, say, former colleagues I met a couple of years ago regarding ZK snarks implemented in a pretty neat way using the JavaScript, so that if you just take the repo, clone it, and make a circuit, and believe me, the circuit looks pretty much like the function in C. So you write your function in C, and then let this text pass through the compiler, get a circuit. So you can just experiment with it to figure out if A plus B actually translates to 1000 depth circuit or something. Of course, I'm joking.
Oh, okay, that's pretty cool. Awesome. Do you know what it's called?
I'm going to share the link in chat.
All right. So it's github.com/idem3/snark.js. So it's Circum.
Circum is a circuit compiler, basically. Well, this stuff is pretty old, but if I recall correctly, when I looked at when I looked into it 2 years ago, it didn't have some features recently added So probably it is a bit over-engineered from the standpoint we need to perceive it, but otherwise it's very useful.
Okay, yeah, thank you for the link. And Adrian, you mentioned that getting randomness is quite easy. I guess when you're doing a secret churn.
Yeah, so like all of this was the research I did when looking in the threshold signature schemes, and so in a lot of cases you go from a Shamir shared secret key to an additive shared by using those Lagrange coefficients. Then like the secret is simply the sum of all shares, or you can consider it that way. And if you're in the setting, then generating random numbers, random secret sharings is easy, because if you set that your local share is simply a random element of the field, and the full secret is a sum of those elements, as long as one party has generated it honestly, then the secret will be random.
Right. Okay, right. Yeah, that makes sense. Thank you for the explanation.
Maybe I can make another small remark. This pertains to the algorithm we discussed today. Obviously, we see how to implement multiplication in a pretty simple way. But at the same time, Gennaro and Goldfeder, in their work in 2018, proposed a completely different way of multiplying two additively shared secrets, which uses poly encryption and multiplication to addition algorithm. So knowing the algorithm we looked at today, I would say I might actually have a question why these people went that complicated way. So probably it has something to do with security. I don't know.
I can answer that actually.
Oh, please, thank you.
So the thing is that this algorithm, which was discussed today, works only if the threshold is quite small. I mean, the t is in particular smaller than n/2, right? Because otherwise, you cannot do this. You cannot reduce the degree of the polynomial, because the degree goes to 2 times t. And if t is larger than n/2, then this is already more than n, and then you cannot reduce the degree. So
okay.
So that's one reason. And if you have large thresholds, in particular in Gennaro Goldfeder, this is like a setting with dishonest majority, then you need this kind of tricks like homomorphic encryption or oblivious transfer, this kind of stuff.
Okay, thank you.
Okay, so it's possible to do with t more than n divided by 2.
Yes,
Like,
and there are multiple
okay.
MPCs. For example, SPDZ works for higher thresholds. There's a lot of schemes for t equal n. Although they actually, I think all of them are using streaks similar as Gennaro. I don't think actually Gennaro invented it. The streaks based on is called multiplication to addition when you translate the shares. I think this is the only way to actually work with higher thresholds, and I'm pretty sure it's older than 218.
Okay.
So do you want to wrap up and choose the volunteer for?
Yeah, we can also
Do
discuss.
we know the topic for next week as well?
Yeah, good question.
I think there are several which would be natural follow-ups. So we could follow up with the next chapter or the skipped chapter in the book, which was related to circuits. Circuits, I mean. Or perhaps this translation thing. It's, I mean, I'm not sure how easy is it to actually present it. It may be just a dictionary of different tricks, and then it's not a great presentation. But that would be an interesting follow-up as well.